And may we begin?
Sure.
Okay, great. All right, once again, a very good morning, good afternoon, good evening, once again, depending on whatever part of the world you're logging in from today. And welcome to the first talk in this month of the Mysteries of the Universe Institute Lecture Series of the Indian Institute of Technology, Roorkee, IIT Roorkee. And this is the 10th in the series. This is MOU ILS-II this year. And we are delighted to have Professor Ramesh Narayan as a distinguished speaker for today. Professor Narayan is the Thomas Dudley Cabot Professor of the Natural Sciences and senior astronomer at the Smithsonian Astrophysical Observatory, Harvard. He is world-renowned for his contributions to high-energy astrophysics, in particular gamma-ray bursts, gravitational lensing, neutron stars, numerical simulations on accretion flows around supermassive black holes, significantly improving upon the GRRMHD, which is General Relativistic Radiative Magnetohydrodynamical Code. He has an incredibly long list of awards and honors. I would venture to mention a few. To begin with, he became a young associate. He got the Young Associate Award of the Indian Academy of Sciences in '83, the Presidential Young Investigator Award of the U.S. National Science Foundation in '89, the W.M. Keck Distinguished Visiting Professor at the Institute for Advanced Study, Princeton. He was elected the Fellow of the Royal Society in 2006, a Fellow of the American Association for the Advancement of Science in 2010. He became the Sackler Visiting Professor at the Institute of Astronomy, Cambridge in 2010, a Distinguished Research Chair at Perimeter Institute, Canada in 2012. He was elected member of the U.S. National Academy of Sciences in 2013, the DST, which is the Department of Science and Technology, Government of India, Indian Institute of Science Centenary Chair Professor at the Indian Institute of Science, India, 2014. He was elected the Fellow of the Third World the World of Academy of Sciences in 2015, an honorary Fellow of the Indian Academy of Sciences in 2016. And I think we are all quite aware of the fact that he has been involved with the incredible Event Horizon Telescope Consortium, and the same has gotten the Diamond Achievement Award by the National Science Foundation US in 2019, the Breakthrough Prize in Fundamental Physics in 2020, the Einstein Medal of the Albert Einstein Society in Bern in 2020, the Bruno Rossi Prize of the American Astronomical Society in 2020, the Nelson P. Jackson Aerospace Award of the National Space Club and Foundation in 2020. He has been a chair or a member of so many advisory, steering, section committees and boards. I will just mention a few. The Institute for Theoretical Physics, UC Santa Barbara, the National Research Council and National Academy of Sciences, US, the National Committee for the International Astronomical Union, the Center for Gravitational Wave Physics, Penn State, the part of the Visiting Committee, the Max Planck Institute for Astrophysics in Germany, the International Review Panel for Cosmology and Gravity Program, the Canadian Institute of Advanced Research, the Royal Society of London, the Visiting Committee of the Department of Astrophysical Sciences, Princeton, the Program Advisory Committee of LIGO, which is the Laser Interferometer Gravitational Wave Observatory, the Scientific Advisory Board for the Math and Physical Sciences Division of the Simons Foundation, the Scientific Advisory Committee of the Perimeter Institute for Theoretical Physics. So with that, I would humbly request Professor Narayan to kindly deliver his lecture. Professor Narayan, please.
Thank you, Professor Mishra. So let me share my screen. And let me know whether this is okay.
It's perfect.
You hear me and you see my slide.
Affirmative to both.
Very good. Good. Thank you, Professor Mishra, for that very kind introduction. And hello, everyone. It's my pleasure to talk to you about a very exciting subject, but also a subject that I am especially excited about and I find extremely interesting: black holes. Specifically, I say astrophysical black holes, by which I mean these are black holes, there are real black holes out there in the universe. Now, this is a very timely topic because, as you all know, just last year, the Nobel Prize in Physics was given to black holes, basically. It was given to Roger Penrose, and this is the citation, for the discovery that black hole formation is a robust prediction of the general theory of relativity, and simultaneously to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. So I will say a little bit about these contributions, but that's not the main point of my talk. But I think for completeness, we should talk about that. So let's start with a little history. See, it all goes back to the so-called general theory of relativity, or what we call general relativity, or GR for short, which Einstein developed in 1915. This was his new theory of gravity, which tried to bring together Newton's gravity theory and special relativity. So it's a relativistic version of gravity, and it's a geometrical theory of gravity. I won't go into the details, but I'm sure you've all heard about curved space-time and all that. These are all very new concepts that he introduced, and this was a way of understanding gravity. So he wrote the equations, the so-called Einstein field equations. They are nonlinear coupled equations. They are tensor equations, actually. Einstein himself did not find an actual solution of those equations. He could only do perturbations, approximate solutions. But within a few weeks after he presented his theory, he presented it in December of the same year, 1915, Schwarzschild discovered the first exact solution of Einstein's equations. And he sent a solution to Einstein, and Einstein said this, he was surprised that anybody could find an exact solution. Not only that, the solution is extremely simple once you've written it down. And so I'm not going to dwell on the details of this equation, but this is the famous Schwarzschild metric. It describes Einstein's gravitational field space-time in the vicinity of a spherically symmetric object. So it's called a metric. It tells you how lengths and time intervals behave. It involves time, space, r, theta, phi. And the only thing that's different from non-gravitational physics, ordinary special relativity, is this factor, 1 minus 2 gm over c squared, r. If you replace this by 1, it's special relativity. You put this factor, it is now general relativity with the parameter m. And as people recognize, and Schwarzschild himself recognized, m here is the mass of your object, g is the gravitational constant, c is the speed of light, r is radius. And this just describes space, vacuum space outside a spherically symmetric object. So if your object has some radius r star, this guy will describe physics at all r greater than r star. Great. You can use this for the Earth, for the Sun, for any spherical object. However, you can ask, what about if I make r really small? You can see from this equation that when r is equal to 2 gm over c squared, something funny happens. The coefficients, this fellow goes to 0, this goes to 1 over 0. There is all sorts of singular behavior. And it took people actually literally decades to understand what this all means. Today, we know what it means. I mean, we have known this now for 60, 70 years. This is the description of a black hole. What's called a Schwarzschild black hole, a spherically symmetric object. And the special radius, 2 gm over c squared, is what is called the radius of the horizon. I'll say a little bit more in the next slide. And furthermore, the theory says if an object shrinks inside this radius, it can no longer remain at rest at that radius. It is forced to shrink all the way down to 0 radius. That's your black hole. So let's talk about the black hole. This is the cartoon picture that everybody knows. Something that's not a black hole is an object with a surface. There's an inside, there's an outside. So this is the Earth, for instance. I can use Schwarzschild metric for the Earth. Just use it outside the surface, and it'll work perfectly well. Inside, I need to do something else. When I have a black hole, what happens is all the mass shrinks down to a point. It's called a singularity. There's no surface, just infinite density sitting in a point of 0 volume. And instead of a surface, what you have is a pseudo surface. kind of a virtual surface. This is the horizon. It's got a radius of 2 gm over c squared. And this surface has this amazing property that things can fall in. You can fall in, you can shine light into it, whatever. But whatever goes in can no longer come out. It's a one-way street. You go in and you're finished. You can never come back on. Outside, in fact, not only can you not come back, you cannot even hang around inside. You're forced to fall into the singularity and become part of the infinite density. So that's the black hole. And this is a specific kind of black hole. This is the Schwarzschild black hole. I'll talk about other black holes as we go along. Okay, singularity, event horizon. Great. Now, okay, so you've got a description of an object with the singularity and all that. Is it real? It's so bizarre. In fact, for a long time, Einstein included, people did not believe that this is actually something that will happen in nature. It's all nice, pretty mathematics, comes from the equations, but surely physics will prevent all these crazy things from happening. And that went on for a long time until 1965, when Penrose, for his Nobel Prize winning work, showed that there are very generic conditions from which, if you start and you follow Einstein's equations, a black hole is guaranteed to form, i.e., there will actually be a singularity of some sort. There will be a horizon of some sort. It will have all the features of the black hole that I described now, and it's almost unavoidable given certain conditions. I'm not going to say more about this. This is actually a mathematical theorem in differential geometry. It's beautiful. It's based on this famous Raychaudhuri equation of 1955. So I would say, wait for next week's talk. I imagine Professor Yao will talk about the Penrose singularity theorem and extensions. The second thing that I would say is, you can ask a more practical question. Can't I stop a black hole from forming by just putting enough pressure in an object so that it refuses to compress under gravity? The answer is no. Again, following general relativity and using what we know about normal matter, what you can show is, if you have a dead object, an object without an internal source of heat to give pressure, if the mass is greater than this quantity, around 2.5 times the mass of the sun, this is the symbol for the mass of the sun, greater than 2.5 times the mass of the sun, it has to become a black hole. There's nothing else it can do. Okay, so we got all of these beautiful results. And as you know, the universe is full of stars. They are born, they die. Some very big stars will die, much more than 2.5 solar masses. They'll probably form black holes when they die. So the universe should have black holes. Can we find them? In fact, we have found huge numbers of black holes in the universe. We have found two categories of black holes. So black holes with masses on the order of 5 to 50 solar masses, it's a range. There are tens of millions of these black holes in each galaxy. These, we are almost certain, every one of them is basically the remnant of a dead star. So each of these was a living star, big, massive living star long ago. It finished its life and it died. And when it died, it had no more heat energy to hold it up. Gravity won, and the thing became a black hole. In addition, at the very center of every galaxy, there is what's called a supermassive black hole. Something with a mass in this range, 10 to the 6 to 10 to the 10 solar masses. There's one, basically, on average, one in the nucleus of each galaxy, right in the center. Exactly how these guys formed is uncertain. I mean, the people have ideas, but we have no, accepted, universally agreed upon formation scenario. Our galaxy, being a typical galaxy, has one of these black holes. Our guy is a relatively small one, 4.2, 10 to the 6 solar masses. And the Nobel Prize, the second two people this year, they got the Nobel Prize for doing beautiful work on this black hole and specifically measuring its mass. So I'm going to spend a couple of minutes talking about how they did this. So how do you measure mass in astrophysics? Ultimately, you use gravity itself to measure mass, right? This is now first year physics, undergraduate physics. Maybe nowadays it's taught even in high school. If I've got a massive object with mass m, and I put a test particle in orbit around it, and I'll make life easy and consider a circular orbit. You know that this particle can go round and round on a stable orbit so long as the gravitational attraction, acceleration inward due to gravity, is balanced by the centrifugal acceleration outward in the frame of this rotating particle. This is the famous equation, gm over r squared is v squared over r, which you can rearrange and you say m is equal to v cubed p over 2 pi g. V is the velocity of the particle in its orbit. P is the period, how long it takes to go around once in the orbit. All these are constants. So if you got a test particle and you can measure its velocity and its period, you're in business. You can measure the mass. The Earth goes around the sun at a speed of 30 kilometers per second in an almost circular orbit. It takes 1 year to go around. You plug these numbers here, you'll find the mass of the Earth, 2 times 10 to the 33 grams. And you can do this to any object in the universe, so long as you have a test particle going around it and you can measure its velocity and period or equivalent quantities. In fact, it won't come as a surprise to you. It doesn't have to be a circular orbit. Kepler told us that the generic orbit is an elliptical orbit, bound orbit, is an elliptical orbit. The whole thing generalizes for an elliptical orbit as well. Very good. So this movie, I believe you saw just a few days ago from Professor Jocelyn Bell Burnell, but I'm going to show it again because it's so beautiful and it's a Nobel Prize. Okay, so this is a kind of a video representation of real data on the region near the center of our galaxy. So what you're seeing right now is the sky. This is the position of the black hole, the star here. Every one of these other dots is a star. And the stars, these are these locations on the sky in the year 1995 point whatever, 1995.5. So when I click this movie, you'll start seeing how the sky changes as a function of time. You'll see time changing from 1995 up to 2020. All these stars will move around. And I want you to just watch what's happening. So let me click. Let's hope it will run. There, very good. So watch all of these stars. So this is a movie based on real data. What people do is they go look at the sky at regular intervals, and then they collect all the data, and then they just follow the trajectory of each star. Notice that they're all going around on these curved tracks. This one is particularly interesting. Look at it. It's finished one ellipse and it's making another ellipse. And okay, I'm going to stop it there. So this particular star has almost finished 2 orbits by now since 1995. Started somewhere here, it went round once, it's gone round again, it's come here. It's a perfect elliptical trajectory. And you can just apply Kepler's laws to this. Once you know the shape of the trajectory and the velocity, etc., you know where the focus is, and you say at the focus, there has to be a massive object. And just like for the circular orbit, if you know all the quantities like velocity, period, etc., you can get the mass. So this particular star says, at this location, there has to be a dark, massive object, 4.2 10 to the 6 solar masses. But it's not just one star. All of these guys are going around. They're not all finishing one orbit, but you can fit every one of them. Look at this guy. Comes like this and it goes off. You can fit its orbit and find out what mass do you require. And every one of these stars gives the same answer. At the focus, 4.2 10 to the 6 solar masses. And that's, we believe, that is the supermassive black hole at the center of our galaxy. A Nobel Prize for the application of nothing more than Kepler's laws and just elementary Newtonian gravity. What made this fantastic is the technology. You know, this is infrared observations. People couldn't do it until the 90s and the 2000s. Technology had to come up, and then the astronomers had to use the technology. It was infrared technology, adaptive optics technology, and of course, a lot of computer applications, etc. Good. That's all I'm going to say about the Nobel Prize. So let's now continue. Now, black hole, we think, is a black object, but astrophysical black holes are often not so black, they're bright. And that's an interesting result. You might wonder, if there's a horizon, why should it be bright? In fact, the horizon itself is not the culprit. These things are bright because gas outside the black hole can radiate. They have what is called an accretion disk, or the process of gas accretion. And this produces radiation, and we observe the radiation. And in fact, some of the brightest objects in the universe are black holes, very counterintuitively. In fact, what you must all have heard of quasars. Quasars are supermassive black holes with accretion around them. In fact, over the history of the universe, pretty much half the radiation produced by any object over the entire history came from a black hole. Okay, good. So let me say a little bit about accretion disks. So here is an artist's impression of what an accretion disk is. So there is a black hole here, right in the middle. This is my disk. So, some gas from somewhere goes into orbit around the black hole, and then slowly it spirals in, closer and closer to the center. Essentially, this gas is falling in to the inside the gravitational potential of the black hole. And as it falls in, it is losing potential energy that has to come out in some other form. A good fraction of that energy comes out as heat. Basically, the gas gets hotter and hotter as it comes to the center. And when it gets very hot, it radiates. And that's the radiation that we observe. This radiation will come out in optical, radio, ultraviolet, X-rays, all sorts of wavelengths. The radiation comes out. And we observe this radiation, and that's how we study black holes. In fact, many of these objects also have what are called jets. Gas comes in, but not all of it falls into the black hole. Some of it comes shooting out in these very narrow collimated beams of material shooting out. And these are called jets, and they're extremely interesting. I'm going to spend about 10, 15 minutes at the end of my talk talking about the jets. But for now, we leave the jets aside. Let's just talk about the accretion itself and the radiation. Okay. So let's talk a little bit about the physics. So I said we start with gas, which has gone into orbit at some large radius from the center. Now this gas, if it's in orbit, has got some angular momentum. And if we assume circular orbits for simplicity, you can easily calculate. The angular momentum per unit mass is square root of gmr, where m is the mass of the black hole, gravitational constant, r is the radius. If I want this gas to come to a smaller radius, and I look at this formula, it must have smaller angular momentum. However, angular momentum is conserved, right? Unless you remove the angular momentum, that piece of gas is not going to come to a smaller radius. It will stick to its own radius wherever it started. We need some mechanism that can take this parcel of gas and keep removing angular momentum from it so that it can come to smaller and smaller radii and finally fall into the black hole. Now, we vaguely call this viscosity because viscosity is a concept that we are familiar with from ordinary physics. Any kind of viscous force will do this for you. It will remove angular momentum and allow the gas to come to the center. But the actual viscosity is not viscosity that we are used to, viscosity of honey or water or any fluid that we consider on Earth. In these systems, the viscosity is provided by magnetic fields. It's in fact provided by what is called MHD turbulence. It is a turbulent motion of the gas that gives up effective viscosity, which causes gas to lose angular momentum. And this goes back to some very famous work, Balbus and Hawley in '91. Okay, I'm going to show a video in a second of what these disks might look like. But let me tell you, how do we model these things? There is considerable analytic work that's being done, which provides a lot of intuition. I'm not going to present any of that. The real problem is very complex. Okay, this is a compressible gas fluid, right? So it's fluid dynamics with compressibility. I've already said magnetic field is critical, so you got to include the magnetic field. This is where MHD comes, magnetohydrodynamics. You have to include the radiation because finally you observe the radiation. And you have to do the whole thing, not in Newtonian space, but in curved space-time, general relativity. It's a very complicated problem. and hard to do it analytically. A lot of work nowadays is done via numerical simulations. So I'm going to show a video. This is not, directly relevant to my talk, but it's a beautiful video. It was made by my postdoctoral fellow, Oleg Sandowski, a few years ago. And I like to show this because it's so nice. So what you should look at here is, there's a black hole right here in the middle. I have an axisymmetric system. So this is showing gas density initially. This is the cross section. This is axisymmetric around the vertical axis. So it's really a torus. If you can see my hand, you probably can't, but it's a torus, which is axisymmetric around the vertical axis. I'm just showing one section. The right-hand side shows gas density. The left-hand side shows some quantities related to radiation. So I'm going to run the movie and just watch. Okay, this is now a simulation of what we think is somewhat realistic physics. We put all the physics we think is important into the system and watch how it evolves. Firstly, the gas started coming in. You saw that, right? This is a black hole. It's falling into the black hole. Some gas is getting ejected out. The whole thing is, beautifully, violently turbulent. In fact, it is this turbulence which is acting like viscosity and allowing the gas to accrete in the first place. The radiation is doing, beautiful dance here. Radiation is coming out. So it's just a lovely illustration of, what these things really might look like if we could go and look at them close up. When you do an analytic model, you simplify all this. You replace all of that turbulence with an effective viscosity. You make various approximations. But anyway, this is the state of the art. This is what you can do using a computer. This is still not what you would observe, because that's what I'm going to come to next. This is what density does as a function of coordinates around the black hole. When you observe this object, you have to include additional effects. In particular, you have to include what is called ray deflection by gravity. So how do I go to the next slide? There. Okay. Okay, now here's a nice little concept that everybody is familiar with, I believe. Gravity can deflect light rays. If I got a massive object like the sun and a ray of light comes past it, it won't continue in a straight line. It'll bend a little bit, not too much. How much it deflects was calculated by Einstein's 1.7 arc seconds. This was a prediction, and it was actually confirmed within a few years. This picture shows this famous so-called eclipse experiment. I won't spend too much time on it, but sitting on Earth, if there is a star out here, which you would normally see in this direction, the straight line here, because the ray is deflected by the sun, it will appear to be coming from here. Because the ray has got deflected, star will appear to have moved in the sky, and it would have been moved by 1.7 arc seconds. Small angle, but measurable. As you come closer and closer to the center of a very massive object, like a
Professor Narayan, you got muted there for a second. I don't know what happened. Sorry.
Yeah, I don't know why, because it said the host muted me.
Oh, okay. I have no idea. Sorry. It was just a few seconds, something happened.
Okay, yeah. So the star will appear to move in the sky by a small amount, 1.7 arc seconds. Now, if I have a black hole and the ray comes very close to the center, the amount of deflection is much more. And in fact, if you come close enough to a black hole, you can find a radius at which, if you send a ray of light, it'll go on a circular orbit around the black hole and come back to you. Okay, it can be an enormous amount of deflection. A full circle can be traced by this one ray of light. In fact, this illustration here is to show you that if you or some very bold adventurer went and sat in a rocket at this radius, and if there was some light coming from the back of this person's head, the light will go all the way around, and this person will look and see the back of his or her head right in front, because the light doesn't go in a straight line, it goes in a circle. Very good. So why is this relevant? This is relevant because if you look at a black hole which is shining, and you look at the central region of the black hole, you won't see what is actually there in the sense of how do things vary as a function of position. What you will see is a distorted image, a very weird distorted image, because whatever light it emits doesn't come to you in a straight line, goes around the black hole and reaches you. So what will you actually see? I will show you. You'll see what's a ring with a dark center. And I'm going to show you here again. It's another of these movies. This is a movie made by my colleague Chikwan Chan. So this is based on a simulation, and it shows what you, an observer, might see if you were to look at this guy, the system, using a wavelength of 3 centimeters. I'm going to show you radio waves, image in radio waves. So if you looked at this object at 3 centimeters, think of this. This is our galactic center black hole, more or less, okay? According to our simulations. You don't see anything particularly interesting. I mean, you see, this is the gas in the accretion disk. This bright region is the beginning of the jet. So there's a jet going out. It's carrying a lot of energy, a lot of radiation. In fact, the jet is very bright, brighter than the accretion disk itself. You don't see the black hole. The black hole is here somewhere, and you don't see it because everything is opaque. At 3 centimeters, it turns out that the accretion gas, the hot gas, is transparent on the outside, but it's opaque on the inside. And all you can see is down to the limit, what is called optical depth unity. So you just see some larger radius. There's no sign of the black hole. I'm going to run this movie. As the movie runs, we are going to change the wavelength from 3 centimeters down to 1 millimeter. And as you go to shorter wavelengths, you can see deeper and deeper into the accretion flow. And by the time you come to 1 millimeter, you can look all the way down to the black hole. So here's the movie, it's running. Okay, we're reducing the wavelength, getting shorter and shorter and shorter. And by this point, you are now beginning to see all the way through. The black hole is here. There is a black region here. That's kind of the location of the black hole. You see a kind of a ring-like feature around it. This ring is created by the deflection of light. I'll show a better picture in a second, okay? I just wanted to show you how things change with wavelengths. And it's just to show you that if you choose the right wavelength, you can look down into the black hole, you can see a ring. But you choose the wrong wavelength, you may get a beautiful picture, but it doesn't show you the black hole. So 1 millimeter is the magic wavelength if you want to study our galactic center black hole. So let's go to the next one. Here is another movie. This was made by my student, Andrew Shale. This, we think, is what the accretion flow around another black hole, M87, might look like if we could look at it with good angular resolution. You see the image. There is a dark region in the middle. That's the so-called shadow. And why is it there? It's there because any light that's reaching us goes around the black hole and comes to us. That is this ring. This ring corresponds to all the rays that went round the black hole before reaching us. So there's a pileup of radiation there. There's all this extra structure. There's all the turbulence and orbit and all sorts of stuff. But there is this beautiful feature, a ring-like feature with a dark center. And this is what is called the shadow of the black hole. This is a real characteristic feature of general relativity operating in the vicinity of a radiating accretion flow around a black hole, right? This is a prediction. Comes all the way from Einstein's relativity. I call it a testable prediction. It says, you go and look at one of these guys under conditions in which it is transparent down to the black hole, and whatever you see, there'll always be a ring-like feature, dark center, and additional stuff which is all related to the accretion. But this ring is not related to accretion. It is gravity, the geometry of gravity. In fact, the diameter of this ring for a Schwarzschild black hole is just given by this formula, 6√3 gm over c squared. Finally, it is related to this phenomenon, fact that photons can go around in circular orbits near a black hole. So that's a prediction, and one would like to go and check this. And as I'm sure many of you know, this was in fact checked and has been verified, but I'm going to show you very briefly how this all happened. So first thing to ask is, which are the best objects for us to go and make this test, looking for a ring? Turns out our own black hole is a very good candidate. It's called Sagittarius A star. It's the center of our galaxy. It's got a mass of 4.2 10 to the 6 solar masses. It's 25,000 light years away. There's another black hole, actually in a different galaxy, some distance away. It's 50 million light years away, much further away. But the black hole is also larger. It's 6 times 10 to the 9 solar masses. And it turns out the numbers work out that these are more or less equally easy or difficult, but they are the best candidates we have. And therefore, this is where one would like to go and observe. Now, it is very challenging. I'll give you some numbers in a second. Basically, what you're saying is, I want to look at an image with a ring like this. The ring has a diameter of 6√3 gm over c squared. And effectively, this ring is sitting at a distance d, where d is either 25,000 light years or 50 million light years. It's a long way, okay? So the angle of this ring is extremely small, and you need a telescope that can resolve that kind of an angular size. Let me remind you, basic physics. Any optical instrument has got a resolution limit. The smallest angle it can resolve is basically 1.22 lambda over d. Ignore the 1.22. It's lambda over d, the wavelength in which you're observing and the diameter of the telescope or instrument. Okay, this is just comes from wave optics. So we know what is the angle we are trying to resolve for our two objects, Sagittarius A star and M87 star. In fact, I'll tell you what the angle is. Angle is as if you're sitting in Roorkee, you're looking at a little ant at the North Pole, and you're trying to make a picture of that ant from the distance of Roorkee, okay? That's a really, in fact, it's not even an ordinary Indian ant. I'm thinking of the tiniest ant on Earth, a 1 millimeter ant. I don't think we have those in India, somewhere else in Southeast Asia. So you put that smallest of small ants in the North Pole and you say, I want to make an image of this guy. Well, going by this formula, as you can imagine, depending on whatever wavelength you use, you need a huge diameter telescope. Bigger the better. And I put some numbers here. If you are trying to do it with meter wave radio, you need a telescope that is as big as 1,000 Earths. If you wanted to do it in millimeter waves, and remember, I said millimeter wave is a good wavelength because you can look down into the black hole. You need a telescope the size of the Earth. And if you want to do it in infrared or light, you need huge, huge telescopes that are way beyond our technical abilities. Fortunately, it turns out that we do effectively have a telescope the size of the Earth. And this was the experiment that was done in the last few years, the so-called Event Horizon Telescope. So I'm going to show a few pictures from the Event Horizon Telescope, but then I want to get on to jets before we run out of time. So what was this? We don't have a telescope that fills the whole Earth. That's impossible. However, using what's called interferometry, you can simulate or try to have something effectively as big as the Earth by using individual telescopes at different locations on the Earth. So here is the Earth. So we have a telescope in Hawaii, one here in Arizona, Mexico, Chile, South Pole, Spain, France. These are all big telescopes, and these are the pictures of these telescopes, which are already there on Earth. They operate at 1 millimeter wavelength. They were built for other reasons. They spend all their time looking at other things in the sky. But if you can get them all to work together and do a really careful experiment, you can combine all of their signals, and through a lot of very advanced technology, you can actually get results equivalent to having a telescope as big as the Earth. And this is what the Event Horizon Telescope did. It brought all these telescopes together, recorded signals. In fact, the signals were recorded individually. Then the tapes were brought to a central place. Computers ran for months correlating the signals. synthesized something that was equivalent to a telescope as big as the Earth, made a picture. Okay. So the first real campaign was in April 2017. Then we repeated the experiment again in 2018. In just about a week, we are going to do the next campaign, 2021. It's always in April. That's when the sky is the right location for these experiments. I'm going to only show you results from April 2017. This is all that's been published so far. The experiment looked at both of these favorable candidates, our galactic center, Sagittarius A star, M87. I'll show you M87 results. This is the result that was released 2 years ago, April 2019. This is the image of the accretion flow around M87, the black hole in M87, measured at 1.3 millimeter wavelength using the Event Horizon Telescope. And it was absolutely amazing. It's exactly what we predicted. There's a nice ring-like structure. There is a dark region in the middle, so-called shadow. And this ring, according to our theory, the model, simulation, everything, is all because of light bending by the black hole. The black hole is sitting somewhere here. Light is bending around it. This is what we observe. Okay, so it was a great success. So very quickly, what did this success actually mean? So we saw the bright ring. We saw the dark central region. We saw the so-called shadow of the black hole. All of this was a major prediction of general relativity. It's a prediction, okay? Nobody had done the experiment before. This was known. This has to happen. You just have to go and look at it. And it absolutely confirmed this very, very quite amazing prediction of general relativity in a very extreme regime of gravity. And it looked great. And for me personally, what was equally interesting was, we were running computer simulations, we and many others. We were all saying, look, this is what it's going to look like. And the thing looked exactly like what we thought it should. I should mention, however, I'll come to this in a second, this is a somewhat blurry picture. Even with all this Earth-sized telescope, there is still a limit to our angular resolution. This is about the angle that we can resolve in the sky. So even though we think there's a very sharp ring here, with this telescope, you cannot resolve the ring, but you can still see the overall morphology and the dark shadow. Okay, well, we know what the diameter of this ring is supposed to be and how it's related to the mass of the black hole. So of course, you can measure the mass of the black hole, 6.5 10 to the 9 solar masses. That comes from that image. There is more stuff you can tell. I won't go into the details. You can tell that this black hole is actually spinning, and it's spinning in the clockwise direction in the sky. We only know the sense of the spin. We do not know how fast it spins, but this is all not for today's talking. Keep it for some other time. Okay, so this is the first experiment, right? And as I said, we have more data, 2018, 2021. We couldn't do on 2020. We were all ready, and then the pandemic came. Telescopes shut down and nobody could go anywhere for observations. This year, we hope enough telescopes will be open that we'll get some good data. And it's going to get better in the future. So what would we like to do next? This is just a still image, right? It's just one stationary image obtained by averaging data over a long period of time. The simulations showed you movies, and we would like to see real movies of this accretion flow around M87 and maybe also the galactic center. We think it can be done. We will need more telescopes. We will need more sensitivity, better technology, but it's all improving all the time. It should be doable in a few years. Our image is blurry. I already told you, even with a telescope as big as the Earth, this is the limit of our angular resolution. If you want to do better, you need an even bigger telescope. And that means you need to go into space. You need to put telescopes into satellites which are going around the Earth or even as far away as the moon or beyond, and then, do interferometry, etc. This would be really amazing. I'm just going to show one, this is all simulations, obviously, and our guess of what is possible. If this panel on the left you consider as the true image, which has got all this fuzzy stuff from the accretion disk and the sharp ring from the photon deflection. If you look at this using our EHT on the ground, this is what the image will look like, which is pretty much what we saw, right? This is the blurred version of this guy. But if you look at the same one with not only the ground, but also a spacecraft outside with more angular resolution, you can hope to get both. You can hope to study both all the accretion physics and also the sharp ring. And the sharp ring, as I told you, is not sensitive to the accretion turbulence or anything. It's just measuring the space-time. It gives you the mass of the black hole. It even gives you the spin of the black hole if you have good enough accuracy. I'm not going to go into that, but this is what one could do. And one could do it for thousands of black holes with enough angular resolution. So that's just kind of a taste of where one might go in the future. But since time is running on, let me go on to my next topic. It's the last topic, and then I'm going to stop today. I've already mentioned spin a few times. So let's talk about spin. Black holes can spin. They don't just have mass, they also have spin. So I'm going to go back again to basics. You have Einstein's equations. You can look for exact solutions of objects with singularities and horizons. Schwarzschild found the first one. That's the so-called Schwarzschild black hole. It corresponds to a non-spinning black hole with one parameter, the mass, m. It's just mass, Newtonian mass, but it's of course in a general relativistic framework. A couple of years after Schwarzschild, Reisner and Nordstrom found another solution where they included electromagnetism. They included both gravity and electromagnetism, same Einstein equations, but extended for electrodynamics. And they found a solution which consists of an object with a mass m and an electric charge q. Still spherically symmetric. It has a singularity. It has a horizon. It's all just like Schwarzschild, but it's got two parameters. So the physics outside this object is determined both by the gravitational mass of the object and the electric charge contained in the object. Good. Then people had to wait a long time, almost 50 years before Kerr discovered the celebrated Kerr metric or the Kerr black hole. So this is another exact solution. This has got again two parameters. But now the second parameter is not electric charge, but it's angular momentum. So this finally represents a spinning black hole. A black hole with a certain amount of mass, m, but also a certain amount of angular momentum, j. And so Kerr's solution describes, it's a generalization of Schwarzschild by means of a second parameter, which is the angular momentum of the object. So that is great. And again, within a couple of years, people included electrodynamics and got finally a solution with three parameters: mass, angular momentum, electric charge. Now, there is something called a no-hair theorem. Physicists call this the no-hair theorem, which says that this is it. There are no more black hole solutions in general relativity. And by that, I mean steady state, not dynamical things. Once they are formed and they're sitting there, more or less unchanging with time, this is it. This is the whole lot of solutions that are possible. There are no more solutions possible. Black holes are extremely simple. Mathematicians will tell you this is still a conjecture. I don't know whether Professor Yao is going to talk about this next week, but it has not been completely proved that this is the complete list of solutions. But as far as we know, this is it, at least in three space dimensions and one time. 3 + 1 dimensions, this is the complete solution. So what we say is, in classical general relativity, black holes are extremely simple. They have a mass, they have a spin, they have a charge. They're just like an elementary particle, right? A proton can have a mass, a spin, and a charge. A black hole, however big it is, can only have these three numbers: mass, spin, and charge. All other details have all washed out. This is all that's left. What is more interesting, when we go to astrophysics, we don't think charge is important, because if anything is charged, there is so much plasma in the universe, other charges will be attracted and the charge will be neutralized. So our astrophysical black holes are even simpler than the classical GR black holes. They only have two numbers, mass and spin. And we like to use a number A star to describe spin. It's defined through this relation. Angular momentum is written as A star times GM squared over C. And the virtue of this is that this number is a dimensionless number, and it can go from 0 to 1. 0 means Schwarzschild black hole. It's not spinning at all. 1 means this is the maximum spin you can give a black hole. Think of it as it's spinning so rapidly that the horizon is going around at the speed of light, very loosely speaking. You can't go faster than that. So there is this range of spin. In any case, this is the second number that we think an astrophysical black hole can have, apart from mass. And this brings up this interesting question. What does spin do? Can we see anything up there in the sky through our observations that is related to spin? Mass itself, we have a very good intuitive feel for mass, right? It goes back to Newton. Mass describes gravity, amount of gravity. If you're at some distance, Newton told us the acceleration is gm over r squared. Einstein will describe this in some different language, curvature of space and all that. But still, it's just a measure of how much gravitational effect an object has got. It determines, for instance, the size of our accretion disk. It determines the size of that photon ring. You remember I said it's 6√3 gm over c squared, so the mass came in. How bright our object gets. This is a fairly straightforward parameter to understand. Spin is a new qualitative effect. It's something that's intrinsic to the black hole that makes it have an angular momentum. It must have some effects, must have some signatures that we can see in astrophysics. Question is, what are these? And have we found them? I'm going to just talk now about jets, because I think there is a good chance that the jets are somehow related to black hole spin. So let me go through the phenomenology here. Very often, when a black hole accretes gas, magnetized gas, it produces also these violent ejections. I showed you the artist's picture, these collimated beams which extend out along the rotation axis. Those beams actually carry gas outward at a very large speed, close to the speed of light, Lorentz factors of several, or even Lorentz factors of 20, 30, 50, hundreds in some special objects, okay? Highly relativistic things. And these jets have been known about now for many decades. People have always wondered, why do they form and where is the power coming from? What is actually pushing these jets out at those enormous speeds? And one of the ideas that's been around now again for many, many years is that it's related to black hole spin. Let's start by looking at some jet pictures. So here is a famous picture of the galaxy Cygnus A in radio waves. So there is a supermassive black hole right here in the middle where my pointer is pointing. I noticed that there is a bit of a time delay in the images that are coming out. But anyway, yeah. And this line out here is the jet. So this has got an accretion disk. It's producing a jet, which goes out a long way. I want to tell you, this black hole is in the middle of the galaxy. The galaxy is about that big. The jet goes out 10 times as big as the galaxy. The scale of this image is probably 10 to the 9 times bigger than the scale of the black hole horizon. Okay, this is a very, very long range structure. These jets, when they form, they go, huge distances, carrying power all the way up to the end. We have, thousands and thousands of these jets in the sky, actually even many more than that. More and more pictures, they're beautiful images. This is M87. The black hole and its ring is right here, which you can observe at 1.3 millimeters. But if you use longer wavelengths and use other telescopes, you see that the same guy has also got a jet which goes a long way out. Again, almost 1 billion times larger scale than the black hole itself. Where are these jets coming from? What is the mechanism that's driving them? We think the mechanism ultimately is what is called the Penrose mechanism, the same Penrose. This is not what they gave him the Nobel Prize for, because this is still unproven. I think it's another Nobel Prize, frankly, if this could all be proved. But what Penrose showed was black holes which are spinning have got some very amazing properties. Firstly, general relativity says, if I've got a spinning object, the space around it also spins, right? So it's a weird concept, but the whole space around the spinning object is being dragged. It's called frame dragging. The whole space is going around with this object because the object is pulling it around as a result of its spin. And Penrose showed that because of this effect, you can do things close to a black hole whereby you can remove energy from the black hole. You can remove energy, you can remove angular momentum. A spinning black hole, you can slow it down. Even though you say, it's got a horizon, how can you do anything to it? But you can. This was Penrose's great insight. You can remove angular momentum, and in the process, you can remove energy. And this is the way of actually extracting energy from a black hole. Now, Penrose had a thought experiment, which, is probably not of practical importance. It's a thought experiment. It's great to explain the physics and the concepts, but it's probably not what nature actually does. But we believe, and this goes back to Blanford and Znayak 77, that a magnetized accretion disk can use similar ideas like Penrose, tap into the frame dragging, and extract energy from the black hole. This has been demonstrated really beautifully in computer simulations. I'm going to show one toy model and one real simulation quickly since we're running out of time. So this toy model is from a paper by Semenov, 2004. Okay, so this guy in the middle here is a spinning black hole. It's spinning around this vertical axis and spinning from left to right, going back, left to right, going back. This is the horizon. This is the magnetic field line, the blue line here. It's embedded in some charged plasma. We don't worry about it. It's not spinning or anything, it's just sitting there. It's being pulled by the black hole. So when I start the movie, it's going to fall in towards the black hole. And normally what you would expect is to just fall in and disappear into the horizon. But let's see if the movie will run. There it goes. Okay, watch what this magnetic field line does. It's coming in. So far, it doesn't even know that the black hole is spinning. But as it comes in and goes into this region, the ergosphere, it knows that it's spinning, and the field line gets pulled in front. Watch, see how it's going? It's pulled in front, goes around behind, comes back, goes around. It's being dragged round and round the black hole, still outside the horizon, but it's being dragged because of the spin and the frame dragging. And the result is, look at the rest of the field line. You see the corkscrew? The corkscrew just keeps flowing out. That's a wave that is going away from the black hole along the axis. It's carrying away angular momentum, it's carrying away energy. It's just a way of visualizing how just dragging of space-time plus an extended field line can enable a system to lose angular momentum and energy along the axis. Okay, I'll just go to the next slide. This is now a full simulation, Tchaikovsky, 2011, but there are many more recent ones, even more impressive. So this is a simulation in 3 dimensions. This is my initial accretion disk, the green stuff. This is a torus, it's orbiting around the black hole, which is in the middle. And as it accretes, it spontaneously produces this jet. And in this movie, Tchaikovsky has very helpfully included what the field lines are doing. And you see the field line goes out exactly like in the previous toy model. But this is, as I say, a much more realistic movie based on a simulation. And this is something that happens quite naturally on the computer. It's, you put a magnetized accretion disk, it wants to do this, so long as the black hole is spinning and so long as there is a magnetic field. In fact, you can show that the power that flows out in the jet scales as square of the magnetic field, square of the spin parameter, and a coefficient which you can calculate. Okay, and the jets carry an enormous amount of power. So, a lot of people believe that this is how the jets are created. Not everybody. Part of the reason is we don't yet have actual observational proof that this actually happens. And this is all I'm going to say, and then I'll stop. So here is the hypothesis that jets are related to black hole spin. Jets are a way by which spinning black holes lose energy and angular momentum and deposit that extra energy and angular momentum back into the universe in the form of these beams of gas and magnetic fields. I would say it's a cosmic manifestation of frame dragging, something that is not present in Newtonian gravity. It comes from general relativity, and a cosmic manifestation on an enormous scale. It's also a demonstration, we think, of this very wonderful concept that black holes, they eat stuff for sure. Everybody knows that. And we all fear black holes because of that. But actually, they're good guys sometimes. They actually can return energy to the outside. A huge amount of energy can come out. But is this all true? How do we actually verify that this is what's going on? I don't have an answer, but I'll tell you what might be a way to do this. End of the day, the jet is being driven by magnetic fields. Magnetic fields going round and round a spinning black hole, dragged around the spinning black hole, carrying away energy and angular momentum. You have to go and observe magnetic fields. How do we look at magnetic fields? It's not so difficult. The radiation that we get from these systems is what is called synchrotron radiation. And synchrotron radiation has this property that it is linearly polarized. And the direction of the polarization, I'm assuming everybody knows what linear polarization is, but the electric vector goes in a direction which is orthogonal to the magnetic field. Okay? So if you can look at the image, but in polarized light, by looking at the direction of polarization, you can tell what was the magnetic field doing at the point of origin of the radiation. And fortunately, the Event Horizon Telescope observed polarization. In 2019, when we published our first results, we did not show the polarization because we were not yet sure about all the calibration. It took another 2 years before we were certain about the results. But this was an image that was released last week. This is the same M87, the same ring, shadow, etc. But this shows not just intensity as a function of position, but also polarization. So this is kind of a fanciful way of showing what is the orientation of the electric field vector of the radiation that we receive. And in fact, the magnetic field is orthogonal to this. So underlying this source, we would say the magnetic field is probably doing something like that. So I won't go into more details, but here's the beginning. We know how to get a handle on magnetic fields. If only we could make movies of both the magnetic field and the intensity, and we could do it with higher resolution with, let us say, a space telescope, and we go and measure the black hole spin, for which there are ideas. With all of those ingredients, one would think we should be able to check whether or not Penrose's idea actually works, Blanford and Znak actually works. When will this happen? I don't know, but I think it's worthwhile. Just to show that energy can come out of a black hole would be an amazing achievement and a final victory, I think, for general relativity. So I'm going to stop here. I just gave you a kind of a taste of all the wonderful things that's going on with black holes. They are basically where general relativity operates at the most extreme limits. You can see physics in the regime of strong gravity. And now with the new technologies that we have, we can actually look way down close to the horizon I think there are so many opportunities there, and we're just at the beginning, we believe, of this whole game. So let me stop here.
Wow, thank you so much, Professor Narayan. I think there could not have been a lovelier talk on astrophysical black holes. Thank you so much. So can we please have a round of applause for Professor Narayan?
Shall I stop sharing?
Yes, please. I think okay, Professor Narayan, can you still hear me?
Yes, I can.
Great. Can we have some questions? I just put them up to you. They've been streaming in the chat session.
Certainly, yeah.
Great. Okay, so let's do that. Okay. All right, so there's a question by Urvashi Arora, and it asks, how do you know the radius or the major axis of an orbit, of the orbit? That's the question.
Yeah, that's actually a good question. So what we see is the star going around in some orbit on the sky. I presume this question was related to the galactic center.
Yes, I believe
now,
so.
the general orbit is an ellipse. We know that. That's Newton's laws and Kepler's laws. If I have one particle going around another mass, in general, it will go on an elliptical orbit with the mass sitting at one of the two foci. Great. Now, if the orbit was entirely in the plane of the sky, i.e., the particle has no motion towards us, it's just going round and round in the sky, then it's very easy. You will see an ellipse, you just look at where is the major axis and you're done. And in fact, once you know the shape of the ellipse, you can even say where is the focus. But of course, that's not the case in the experiment I showed. The typical star will be going in an elliptical orbit, but it'll usually be tilted. It could be tilted off the plane of the sky, and the major axis could be tilted away from the plane of the sky. So it could be in some three-dimensional orientation. So the question is, how do we get from that the actual shape of the orbit? The answer is just knowing the shape of the orbit is not enough. You also need to know velocity, how it is moving as a function of time along the orbit. And if you think about it a little bit, you can convince yourself that that gives you enough information to solve for all the numbers describing the orbit. So in fact, you can calculate what is the true major axis, which way it is oriented, where the focus is located, where would it appear on the sky, etc. So yeah, so it is just like for the test particle in a circular orbit, just knowing the orbit shape is not enough. You need the velocity as well, two numbers. So here you just have to look at the time evolution of that orbit, then you can solve for it.
Okay, great. So, so there's a question by Sankalp Chaudhary. The question is, in the animation of stars around galactic centers, did they not observe any precession in the trajectory of the nearest star? You mentioned perfectly elliptical path, or was the error bar or resolution greater than any observable precession?
Oh, wow, wonderful question. Yep. This has been a long-standing goal. So for the general audience, let me explain. Newton's gravity says that the orbit is a perfect ellipse. But once you go to general relativity, one can show that the general orbit is not a perfect ellipse, but actually it's a precessing ellipse. So as a function of time, the major axis will act slowly kind of rotate. And in fact, it depends, there are lots of details there. But anyway, it's not a perfect ellipse. So if you have enough accuracy, you should be able to see that the second time round, the orbit didn't go exactly where the first one went, but got shifted a little bit. Now, the amount of shift depends on how tight the orbit is. If the orbit is very close to the black hole, it precesses a huge amount. These stars don't precess that much, but they do precess. We do expect them to precess, and we do expect to be able to see it. At the moment, it has not yet been convincingly observed. It's a matter of accuracy, exactly as the question asked. The precision is not yet there to show that the second orbit, or in the future, the third orbit, is shifted from the first orbit by the predicted amount. There is an extra complication. It's not just the precision. While these stars are going around, remember there are other stars which are also moving around, and they are exerting accelerations on your primary star. So there are extra perturbations. It's not like you have just one test particle all by itself around the black hole. There are other test particles, they have some mass, they pull and push this guy. So you have to allow for that. And it's conceivable that that might interfere with your ability to measure this. In any case, the short answer is people are hoping to measure it. They might be able to measure it pretty soon. They're at the edge right now. But there is a possibility that there may be some extra noise to worry about.
Great. So there's a question by Ganesh Subramaniam, and the question is, from the video shown, it can be seen that supermassive black holes are not eating up any stars. It is supposed to eat up some stars, which might have been observed. Could you please explain?
Yeah, okay. So the stars I showed you, the ones in our galactic center, they are still sufficiently far away from the black hole. They're just going around in these so-called geodesic orbits, just go round and round. And as we talked just now, may not be a perfect ellipse, it may be slightly precessing, but it's like the Earth going around the sun. The sun doesn't eat up the Earth. We have been here for billions of years, no problem. However, if you have a star that comes closer to the black hole, say within a few horizon radii, or even a few tens of horizon radii in some cases, then what can happen is the star can be pulled apart by the so-called tidal force of the black hole. So this nice spherical object will get stretched by the gravity and can actually get destroyed. It gets pulled apart, and then what happens is, then as the question asked, this star can fall into the black hole. The destroyed star, half of it will fall into the black hole, and half of it, it's believed, will escape. And the half that falls in will actually fall in through an accretion disk, because it still has angular momentum. So it'll go into orbit, it'll form an accretion disk. All the stuff I showed you will happen. The gas will fall into the black hole, might produce a jet. All that should happen. Right now, our galactic center is not doing it, but it must have done this to some occasional stars in the past. The numbers that I have seen is that this should happen perhaps once every, I want to say, 1,000,000 years, or maybe 100,000 years in each galaxy. So our galaxy maybe 100,000 years ago did this. And there must have been a period when it was very bright because it was eating a star, but it only happens occasionally and it doesn't live very long. It'll become very bright, and in a few months or a year, it'll die down again because it's eaten up everything. This has been seen around other galaxies. By now, maybe there's about a couple of dozen of these events that have been seen, and it's expected that in the next few years, we will see thousands of these events. Not in our galaxy, but in other galaxies, thousands and thousands with the telescopes that are coming up.
Great. So next up is a query by Agaz Mahajan, and it basically asks, even though numerical methods are needed, are we sure there are no analytical methods for solving the problems? So he's interested in asking, can we not have an exact solution like the Schwarzschild solution in this program?
Yeah, the field started with analytic solutions. Obviously, we didn't have the computers in the early days. To get analytic solutions, you have to make approximations. So for instance, one approximation is you say, I don't worry about the vertical structure of the disk. I will replace this complicated turbulent accretion disk with just a sheet of zero thickness going around the black hole, and I'll give the sheet properties that are reflective of the whole disk. I'll replace the turbulence with some effective viscosity, some numbers, etc. I will replace all the complicated structure, axisymmetric structure, non-axisymmetric structure with an axisymmetric approximation. So you can do these things and you can get nice solutions. And these are well known, they are in textbooks, and they are what one would normally use to get a quick idea of what to expect from any given system. But they will miss certain parts of the physics. For instance, if you've got a system with both inflowing gas and outflowing gas, that's difficult to model with an infinitely thin sheet. You need to include the vertical direction to get the outflow. If you want to do the magnetic field and how it gets frame dragged, etc., you need to go beyond the simplest models. So what I would say is the analytic models are extremely useful. They give huge amount of intuition. People continue to look for them and work with them. I like them myself. I use them a lot. But if you want to try and be a little more realistic, simulations are the way to go. End of the day, simulations can include more physics, but they can only include the physics you include, right? So you never know whether you've got all the features you need, but you can keep experimenting and trying to do better and better, and you always have the observations for comparison. So I'm not going to say that one is better than the other. It's just that we have a new tool now, we can use this, but analytic work is always valuable.
Okay, so there's a question, a second one by Urvashi Arora, and she asks, if we use interferometer, larger the baseline, larger would be the noise. So how can you overcome all such noises? Because in this case, the baseline is very large.
Yes, this is why this experiment is so difficult. So, let's look at the Event Horizon Telescope. We did not have a telescope as big as the Earth. Instead, we had 8 tiny telescopes located in different regions of the Earth, collecting tiny amounts of information, each of them, right, compared to the whole Earth. So what do we lose? I mean, we are getting still the angular resolution. So, Urvashi's question is very good. Good, you've got big baseline, you've got angular resolution, but you have to lose something, right? I mean, you don't have the whole Earth. What you're losing is sensitivity. A telescope, a single telescope as big as the Earth can collect a huge amount of signal. You can get an, extremely precise, beautiful image. You cannot do it with just 8 little telescopes located all around the Earth. You have to fight really hard against noise, mainly because, you just don't have enough information. So the way to get over it is to make your telescopes as perfect as you can. You increase the so-called bandwidth. So when you look at 1.3 millimeters, which is 230 gigahertz, you don't observe only at 230 gigahertz, you observe over a range of frequencies around 230 gigahertz. And the broader you can go, the more data you're collecting, because each little wavelength range is giving you independent information about the object. So the name of the game here is to reduce the noise in the instruments itself, increase the bandwidth as much as you can go, which is all technologies and also computer technology. You have to save the data. And this is data coming at an enormous bit rate. But yeah, so that's where the field is going, trying to go for larger bandwidths. And already I can tell you, between 2017 and 2021, the bandwidth has gone up because we got better instruments now. There are a few more telescopes. We have a telescope in Greenland, which was not present in 2017, but now it is there. It's going to collect data in a week from now. So yeah, so the answer is better instruments, better bandwidth, more telescopes. But at the end of the day, you're always limited by noise.
All right. So there's a question by Adrit Ravichandran, and the question is: since black holes are spherically symmetric systems, shouldn't the accretion material also be a spherical shell rather than a disk? And hence, shouldn't the black portion of the black holes be invisible to telescopes?
Okay, I'm not sure I got the last bit, but let's talk about the first bit. Okay, so the black hole, at least the Schwarzschild black hole, is completely spherically symmetric. So its gravitational field is, independent of orientation. It's the same gravitational attraction in any direction you go. Accretion disk is not spherically symmetric, and that's because it has angular momentum. So the angular momentum, which is a vector, that tells you the orientation of the axis of the orbit. If the orbit is going around my black hole in some orbital plane, the perpendicular to that plane shows the direction of the angular momentum. So the material has a vector associated with it, the angular momentum. That is what drives it to go into a disk-like shape rather than a spherical shape. Suppose you artificially set up a system with a spherically symmetric black hole, and you put gas around it without any angular momentum, gas at rest, and then let the gas fall. What you say will happen? Everything will fall in because they'll all have the same pull. There's no centrifugal force to worry about. You will get what is called spherical accretion. Every gas streamline will fall in radially. Assuming this guy gets hot and radiates, what you will see is a spherically symmetric distribution of emission. But assuming it is transparent, the image will still have this ring shape. And this is something many people have shown, that you can start with a completely spherically symmetric accretion flow. And if you could take an image of that object, you will still see a ring. And if it's a Schwarzschild black hole, the ring will have a diameter of 6 square root of 3 gm over c squared. And all of the things I told you will still happen. Those things don't matter. What is the exact shape of the accretion disk? It's a feature of the gravity. Now, you asked something about won't the black hole be invisible? The answer is yes. If the accretion flow is opaque, optically thick, in the technical language we use, you cannot look down into the black hole. You will see the accretion flow. It'll be kind of a, more or less spherical object. You'll see down to some surface. The black hole is hidden inside. You can't see it. But presumably, if you go to some other wavelength, which is where it's transparent, you will see the black hole and you'll see the ring and you'll see all that I talked about.
Okay, there's a query by Kiwi Liang, and it says, will the mass of the black hole in the center change the wavelength to see the ring? Does that imply for these two candidates, the observation wavelength would be different?
Yeah, in principle, for each object, you could have a different optimal wavelength for observing the ring in the image. By some accident that I won't go into, it turns out that the same wavelength, 1.3 millimeters, works for both our galactic center black hole and for the black hole in M87. And in fact, calculations suggest that that's going to be a good wave, 1.3 millimeters or shorter. 0.86 millimeters is where the technology is headed next. It has certain advantages and maybe go even shorter in the future. This range of wavelengths at around a millimeter appear to be optimal, not just for these two, but for a host of other black hole systems, which we could observe in the future if we could get even larger angular resolution. So yeah, so the answer is in principle, yes, but fortunately, it turns out that roughly the same wavelength range will work for a wide range of objects.
Okay. Lai Chi Long has a couple of queries. So the first is, how many modes of dynamics at the event horizon of the black hole can we capture and understand in practice and in principle?
Modes of dynamics. I'm not sure exactly what that means, but let me try and answer it. All of the studies I told you, and in fact, all of these black holes that we study in astrophysics, these are all stationary black holes. There is no dynamics left over. They are just sitting there. They have a certain space-time around them. The space-time is independent of time, right? There's no dynamics. There's no time variations in the space-time itself. There is a lot of dynamics in the gas, in the magnetic field, in the jets. All of that is happening, but it's all happening in a space-time background, which is completely unchanging in time. Okay? Now, this is not necessarily the case for all experiments. This is a whole other topic, gravitational waves, which I don't know if you've had a talk or not on that, but as you know, LIGO and other interferometers have observed gravitational waves from merging black holes. Those are highly dynamical situations. Those black holes are not just sitting there with a fixed space-time. The space-time is changing quite rapidly as they come together and merge and do stuff. Very dynamical space-times. And in fact, the gravitational waves are produced by all of the dynamics. Moreover, after the black hole is formed, there is a so-called ring down. The last few pieces of signal that come out, they come out with certain characteristic frequencies which are related to the modes, the dynamical modes of the black hole. The finally formed black hole is kind of, it's ringing like a bell, and all those ringing notes are coming out as gravitational waves. So I think if you want to look at dynamics of the space-time, the experiments I told you about are not the place. Gravitational waves, that's where the future is for that business. We are working with completely time-independent space-times. But we are looking at the dynamics of the gas. We are looking at the propagation of photons. We are looking at this ring formation. So these are kind of different looks at strong gravity.
All right, there was a part two of that, which probably you've kind of already addressed, but still it basically asks specifically about the dynamics of mass and spin coupling behavior.
I'm not sure I know what that question means. So,
okay.
I told you how for the metrics that we are looking at, the Kerr metric or the Schwarzschild metric, how the mass and the spin couple to the gas. In particular, jets. Jets can be produced by the spin, the frame dragging. If you want to look at dynamical spacetimes with mass and spin, as I said, you should go and look at gravitational wave producing systems.
Okay, so there is a query by Devika PB, and the query is, if the black hole spins rapidly and it produces pulsations, if the pulsations grow stronger, can they tear the black hole apart?
So you can merge two black holes and make a single black hole. In fact, if you take two black holes, let's say initially they're not spinning, but they're in orbit around each other. So they're going around each other and they come closer together and merge. The final black hole you form will be a spinning black hole because it will take all the angular momentum that was present and it'll become a spinning black hole. It still won't be spinning at the maximum in terms of this A star parameter. It may be around 0.7, 0.8, whatever. It won't be 1. You can do other things and maybe you can spin up a black hole more and more and more. And maybe you can push this A star parameter close to the limit 1. But you can show that there is really no way in which you can push the black hole above 1. It's a limit. However much you try to spin up the black hole with any mechanism you can think of, you will change the mass and angular momentum in such a way that the A star parameter will always be less than or equal to 1. Okay, so that's the first answer. So you might think, if I could push it above 1, this black hole can do nothing but split apart. I think that was the spirit of the question you were asking. You cannot spin it that much. But you can ask more generally, can I take a black hole, spinning or otherwise, and just split it and make 2 black holes? After all, I took the 2 black holes and brought them in and made 1 black hole. Why can't I reverse this? This is the whole business of black holes, the horizon, one-way membrane and all that. Things go happily in one direction. You can take 2 black holes and make 1. You can't take 1 black hole and just split it into 2. It's just not possible. There are very deep theorems. These are all mathematical theorems which have been proved. Hawking in particular proved the so-called area theorem. The area will only increase as a function of time. And to take a single black hole and make 2 black holes, you'll have to decrease the total area of the horizon, and you just can't do it. So the answer is no. Nobody has found a way of starting with 1 black hole and splitting it up into multiple black holes. Whereas the converse, easy. In fact, LIGO is seeing this. Every object they look at, they are looking at 2 black holes which are merging to make 1. So that's happening all the time in the universe. But physics tells us the opposite will never happen.
Great. Alex has a pair of queries. The first is, when the light very close to the black hole is just going round and round about it and is thus trapped, how come we are able to see the accretion rings around it? That's the first. The second is the C.K. Chan's simulation that you showed. In that, how is the simulation changing with the changing wavelength?
Okay, so the first part. So I told you that there is a special radius around the black hole where if I send a photon in the tangential direction, it'll just go around the black hole and it'll come back to the starting place. And, if you do everything perfectly, it can go round and round many, many times. However, I did not tell you the following, but now I'll tell you. This is what is called an unstable orbit. i.e., if I took this photon, which is on this circular orbit, and perturb it the slightest amount, it will not remain on this closed orbit. Let us say it's going round tangentially, and I just push it out a little bit. If I push it out the tiniest amount, what will happen is it'll try to go around, but it'll get further and further away from the black hole, and finally it'll escape. If I take that initial photon and push it slightly inward, it'll go around the black hole and fall into the horizon. So it's an unstable orbit. It separates orbits that escape, which you and I as an observer can detect, and orbits that fall into the black hole that we will never see because the radiation is gone. So when I showed those movies, the way those movies are made, you look at all photons emitted by the gas in all directions. Many of those photons actually just fall into the black hole and disappear. We never get a chance to see them. But then there are lots of them which actually escape. And there is a bunch of them which go close to this special orbit, maybe go around a couple of times and then reach us. Those are the guys that finally form that sharp ring. So that is how you form the ring. So the point is, you can never actually have an orbit that goes round and round forever. That is infinitely unstable. All orbits either get out or fall in, but they pile up near this particular unstable orbit. Okay, the second question was, what was that movie the C.K. Chan movie, where I showed as a function of wavelength, how the accretion gas became more and more transparent. So what was going on there is the following. A simulation was run. A three-dimensional, full MHD simulation was run on the computer, and it was saved. From the simulation, you can calculate what is the radiation that will escape, what will you see, and you can do that calculation for any wavelength you choose. So what CK did in that particular movie is he took the simulation, he ran the simulation. During post-processing, he just said, as a function of time, I will just dial down the wavelength. Starting at 3 centimeters, I'll come all the way down to 1.3 millimeters. So it's the same simulation it's running. It's a dynamical simulation, but you're looking at it as if you have a filter in your eye, which initially is looking at the 3 centimeter radiation, and then the filter keeps changing. And towards the end, you're looking at the same object, the same dynamical object at 1.3 millimeters. This is all done in post-processing. And he has a very fast code that can do this using GPUs and all that.
Okay, there's a question by Vanshaj Karni, and it says, as shown in the simulations, the magnetic field lines, they go around a black hole and in turn become the jets that come out. Does that mean that the jets are rather temporary? It's a temporary phenomenon rather than permanent feature of a black hole?
It's a very good question. Yeah. So I can tell you from the observational point of view, there are some black holes which will have jets at some times. Other times they don't have a jet, or at least nothing that we can observe. Maybe a little weak jet, but it's too weak for us to see. So you can have a strong jet for a while, no jet afterwards, then it may come back, etc. Even the ones that have got a jet pretty much all the time, they are kind of blobby. It's not a continuous structure on the sky. It's as if, sometimes it gets brighter, sometimes it's dimmer. So you can have variations along the jet. Or if you look at the center, the brightness may go up and down. So it's clear that these are time variable structures. And the question you were asking was, could it be that the magnetic field sometimes is there and give you a jet? Maybe other times you don't have a magnetic field and the jet goes away. I don't think we really know the answer to that. In the computer simulations, we set up things so that once the jet forms, there is a magnetic field pretty much all the time. And even those systems which have a magnetic field all the time, their power can vary as a function of time because of all the turbulence in the disk. But you can also set up simulations where the field can turn on and off, and those clearly show that the jets can come and go. So this is a detailed question which depends on exactly what an accretion disk is doing, what the magnetic field in the disk is doing, what's the topology of the magnetic field. Is it highly, crumpled up and scrambled, or is it organized so that it can make a big jet? These are all open questions, and perhaps, the kind of observations that I was describing will give us a better handle on what's going on in these systems. But I would say at the moment we don't know, but your guess is a pretty good one, that the magnetic field may actually change as a function of time, and that may be reflected in the jet.
Okay, so the last pair of queries by Samik. So the query is, in GR-MHD simulations, if I understand correctly, what has been written is that the electron-ion interactions are not included. So the question is, if we include them, will the image be better? That's the first query. The second is, how does the mass of the black hole affect the magnetic field values?
Good. Yes, so let's do the first part. I used MHD, and we all use MHD. It's a relatively easy approximation of plasmas, which can be handled on the computer. You're treating this magnetized plasma essentially as a gas, which has got embedded magnetic fields. So it's a particular approximation of a real plasma fluid. We think it's good enough for many purposes, but of course it doesn't capture all of the complicated physics in the gas. In particular, all of these accretion systems and jets, they are plasmas, which means that at the microscopic level, you've got protons and electrons. Or in fact, just to kind of throw it out there, it is quite possible that some of the jets actually have electron-positron plasmas, not protons. They're actually pairs. So it doesn't matter, okay? So there are these particles, and there's a lot of plasma physics associated with that, which is all kind of hidden under the rug when we do magnetohydrodynamics, MHD. So it's the hope, and with some kind of good reason, that doing just bulk gas dynamics through MHD approximation is good enough. There are theorists who are looking into what will the detailed plasma physics do. For instance, the question was, will that give us a better image or a better understanding of the radiation? For sure, the radiation comes only from the electrons. And you need to understand what the electrons are doing compared to what the protons are doing to know what the radiation will do. Those are all being approximated at the moment. Hopefully in the future, this can be done better. Very good. Now, what was the second part of the question? I've forgotten now. Something about.
So how does the mass of the black hole affect the magnetic field values of the black hole? So
Good. So in principle, the magnetic field is one parameter, and it may have nothing at all to do with the black hole mass. In practice, in fact, they are coupled together because these systems reach something called equipartition. That is to say, the energy density in the gas, energy density in the magnetic field, etc., they all come into equilibrium. This is complicated nonlinear physics, but there is a sense in which these systems have certain characteristic magnetic field strengths or gas pressure or temperature. These things are not completely decoupled from the size of the system or the mass of the system. So as a rule, you can cross compare a black hole with 50 solar mass, 10 to the 6 solar mass, 10 to the 9 solar mass at what I would call similar states. And you can pretty much kind of translate something like a field strength here to the field strength there to the field strength there. There are scaling relations which actually apply fairly well. So in practice, we pretty much know what the field strength is going to be for each of these systems. I won't go into more details, okay? But it's a good question. But as I say, in practice, it is not a totally independent parameter. It is tied to the mass end of the day due to these nonlinear couplings.
All right, thank you so much, Professor Narayan, for that for that incredible patience with a fairly long list of queries. So I would thank you once again so much for agreeing to give this beautiful talk. Thank you so much once again. And with this, we come to the conclusion of today's session. Thanks to everybody for joining in, and stay safe. So bye-bye.
Thank you. Bye.
Yeah, please fill in the response forms. I keep forgetting to request everybody. The team is putting up reminders. Yeah. So all right, thanks once again. Please tune in next Saturday for the next installment in the series. All right, once again, bye. Have a good weekend. Yeah, I'm ending the meeting, team.